So on this question here, we're looking to find the minimum speed the roller coaster has to attain in order to stay in the circle. All right? Now, if it does that, and they show this in the diagram, the only force acting on the roller coaster will be the force of gravity. Okay? We won't have any normal force because if we're going just fast enough to stay in the circle, we don't push on the track. If we don't push on the track doesn't push back, and thus there's no reactive or normal force. So, in this case then, since gravity is acting towards the center of the circle, and there are no other forces, forces in minus forces out means that the centripetal force is being provided by the force of gravity alone. That's going to mean mv squared over r equals m times g. Now I want to solve for the minimum speed, so I'm solving for v. When I do that, I'm going to multiply both sides by r. M is going to cancel, and I'm going to square root. Okay? V, the minimum speed in this case, right, is going to be 9.81 times 50. Sorry, it's a diameter of 50, isn't it? So if radius is 25. Is that what you're going to tell me, Robert? Because you were paying attention when you caught that, and I didn't. Okay. So 25 is our radius. Okay, so when we do that, okay, we're going to have 9.81 times 25, and then we square root that. All right, so we're looking at a minimum speed here of 15.7 meters per second. Okay, that would be the minimum speed required to stay in that loop. We all right with that? Okay, so the thing we have to remember, most important thing we have to remember about vertical circles, okay, is that the centripetal force is like the net force. It's forces in minus forces out. That means on every single vertical circular motion problem you do, you should draw a free body diagram. Okay? If we're talking about an object that is going under the loop, okay, like in that position there, okay, then we know that there would definitely be a force of gravity, and there could possibly be a normal force. If we're going faster than the minimum speed, then there would be a normal force there. If we're not, then there's just going to be Fg. Right? We have this situation going over the top of a vertical circle. Okay? In that situation, Fg is acting into the circle, and as long as we're not going too fast, what will be acting out? Normal force. If we are going fast enough, that normal force will equal 0, because we'll lose contact with the surface and we'll feel weightless. Okay. The other situation we talked about is this one. Okay, bottom of the vertical circle. Now, gravity is pulling this way. Well, it's still the same way, down. It just now happens to be out of the circle. Okay, because gravity's pulling me into the edge of the circle and my inertia is also doing that, what's this force? Fn. And it's really big in that situation. That is where you will always feel the heaviest for a couple of reasons. It's where you're going to be going the fastest. It's the bottom of the circle. Okay? And it's where all the forces act together to push on you. Okay? Making you feel heavier. Normal force will always be largest at the bottom of the circle. So when you ride the Mindbender next week, okay, you're going to feel heavy all the way through the loops, but you'll feel heaviest at the bottom. Okay? Now, you'll feel heavy all the way through because the Mindbender goes way faster than the minimum speed required to stay in the loop. Okay? In fact, as you go through the loops, you will feel G-forces anywhere between 3 and 5 Gs. Okay? So like the first time you ride the Mindbender, you will ride it with your head in this position. Your chin will literally be stuck to your chest, okay? Because your head will be so heavy, and you just won't be ready for it, okay? The first time. As you go through those loops, everyone's just like, this is fun, okay? And their head is just like stuck to their chest. okay, because their head is so heavy and they're just not ready for it. Okay, the second time they'll kind of brace for it and they'll have their eyes a little more open, okay, and kind of see more things. So you should definitely ride the Mindbender more than one time. Okay? All right, does that make sense? Those three places. Why didn't we talk about this place? Because you can't stay there. Okay? If that's a roller coaster or a track, how do you stay there? You have to have wheels on the other side. Now, if they did do that, then this is the world's most dangerous roller coaster, and it would be lawsuit after lawsuit. Okay? Instead of feeling like all the blood is rushing out of your head, like you would here it would all rush, into your head. That would kill you. Okay? See, in this situation, you experience what we call positive G-forces. That is, you feel heavier than normal, and things kind of drain away from your head. Your body can withstand large numbers of positive G-forces, provided it's not for too long. Your body cannot withstand what we call negative G-forces. Okay? And that means that basically your apparent weight is working opposite to gravity. Okay? And so you're feeling kind of lighter, and in this case, all the blood would rush to your head. What will happen then? Yeah, you'll have a stroke. Exactly. You'll have an aneurysm. The blood vessels in your brain and your eyes and your head will break. They're not designed to bear the weight of blood that is many times heavier than normal. Okay? You have these tiny little capillaries and veins in your brain. Okay? If those break, you bleed into your brain. Okay? That's a stroke. You don't want that. It's very bad for you. Okay? It could also lead to breaking capillaries in your eyes. Okay? How many people have ever had like a blood vessel in their eye that burst? Okay? It happens sometimes. You get that kind of red spot on your eye. That would happen, like you have a lot of that. You could actually have bleeding within the eye. Okay? That looks really gross, by the way. If you've ever seen someone that's had that happen, like the retina's detached, their eye looks really red, even through the pupil. It's kind of freaky looking. Okay? So we wouldn't want that. Okay? You don't want to pull negative G-forces. It's very, very hard on your body and can be fatal. Even as low as 2 or 3 negative Gs could be very, very bad for you. Okay? Fighter pilots have to watch out for this because they can do these. If they fly through a loop with the plane upside down, that's what will happen. Okay? Their suits won't help them in that case. Okay? Those inflatable suits that they had. Okay? Those will not help them here. Negative G-forces can kill you. Okay? So you want to avoid those. That's why we don't deal with that situation, because if this was just a hill and not a track or something like that, you'd just fall off. You can't really go under the bottom of a vertical circle. All right, so those are the situations that we need to be familiar with. We need to remember that FC equals forces in minus forces out for a vertical circle. We have to remember that Fn is often referred to as apparent weight. Okay? Those are the things we have to remember for vertical circles. Okay, since we just did a minimum speed one, don't forget about that one. But let's look at number 2. What's the radius of a roller coaster loop if a car can go around it with a speed of 20 meters per second? Okay, so it can go around safely at 20 meters per second. Okay? Now, the only part of a loop where you have to worry about your safety is which part of it? The top on the inside. You can't fall off the top. Okay? If I don't have enough speed to go over the top of the hill, I just roll back down. No harm, no foul. Okay? But if I don't go fast enough in here, I fall. Die. That's bad. Okay? So we're talking about the inside at the top of the vertical circle. See if you can calculate the radius. It's going just fast enough to stay in the circle. So on number 2, okay, they're telling us find the radius of this circle, knowing that the minimum speed of the circle is 20.0 meters per second. Okay, so if this thing is going at the minimum speed, the only force acting on it is the force of gravity, and thus forces in is gravity, forces out is nothing, and so Fc equals G. Okay, there's only one force acting, and it's acting directly into the middle as a centripetal force. So mv squared over r equals m times g, and we're looking for r. So we're going to multiply both sides by r, then we're going to divide both sides by m times g, which makes the m's cancel. Okay? And so what we'll be left with here is v squared over g equals r. So that'll be 20 squared divided by 9.81, and that'll give us our 40.8 meters. Questions on that one? Okay. So for these questions, the situation, being able to interpret and visualize the situation is important, just like it was in the last unit where you had to be able to, kind of picture what was going on in the question. That's still important here. Luckily, though, there aren't nearly as many forces present in these types of questions. Okay, I used to do this demo in class, where I would fill a bucket with water, and then I would whirl it around and around in a vertical circle and not get wet. Problem is they don't make buckets like they used to. Okay? Buckets used to be like really strong plastic with a metal handle. Now they're really cheap plastic with a really cheap plastic handle. Okay? Have you ever seen like an ice cream pail now? Okay? You whirl that thing around with any amount of water in it and the handle breaks off. Okay? And when the handle breaks, what is the path followed by the bucket of water? A straight line. Not good. Okay, because where is it going to break? When I'm whirling that thing around and around the circle, where's it going to break? Right at the bottom. So just as I'm getting to the bottom and starting to come up, that's when the handle breaks. So the bucket flies off like this, okay, and narrowly misses the head of the person sitting right here, where tail is, and splatters all over the wall. So we don't do that demo anymore. We don't have any good buckets. Right? But you could do this. If you were at home and there was no one around, you were outside, and no one would get hurt. Okay? You could try this one at home. If you whirl that bucket around and around the circle fast enough, none of the water will come out. Okay? Because its inertia will keep it pinned to the bottom of the bucket. Okay? Whether that bucket is at the side or at the top or at the bottom, the water will be pinned to the inside of the bucket. Okay? So we have this bucket of water with a mass of 1.5 kilograms being spun in a vertical circle on a rope. Okay, the radius of the circle is 0.75 meters. The speed of the bucket is 3 meters per second. What is the tension in the rope at position C? So the bottom of the loop. Right? Now, they've been nice and done the free body diagram for us. They're saying force of gravity is acting out, and the tension, which because it's on a rope replaces normal force, is acting in. Okay, everybody all right with that? Right, if you don't have a track, you can't have normal force. Something's on a rope, okay, then it's the tension in the rope that's pulling back towards the middle. All right, so if I'm looking at this vertical circle, forces in minus forces out for this one looks like this. Fc equals the tension in the rope minus the force of gravity. What I'm trying to find? I'm looking for the tension in the rope. Okay, if I want to get the tension in the rope by itself, what do I do with Fg? Add it over to the other side. Okay, now that should make sense. If I add these two forces together, that should make the tension really what? Yeah, big. Yeah, okay, really tight, big, bigger. Okay, isn't the bottom where we're supposed to feel the heaviest? Then that's also where the bucket should feel the heaviest if you were swinging it around on a rope. Okay, it should feel the heaviest there at the bottom. All right, so I've got Fc plus Fg equals the tension in the rope. So that's going to be mv squared over r plus m times g equals t. So 1.5 times 3 squared, if it was the speed of the bucket was 3 meters per second, divided by the radius, 0.75, plus 1.5 times 9.81. Force of gravity. Okay, so there's my centripetal force plus 1.5 times 9.81. All right, so we're looking at a tension in the rope of 33 newtons. Only two significant figures in this question. Everybody all right with how that one works? Okay, this is kind of where the questions are headed. Okay, they're going to ask you to calculate one of the, like the force in or the force out, or some part of the force in or the force out. Okay, that's where these questions are going to be headed to. All right, so let's have you guys try question number 1. You don't have to do number 2. We'll talk about number 2. Okay, and then try number 3 as well. Okay, so 1 and 3 here for right now. So for question number 1, they're wanting us to calculate the tension in the rope at the top of the circle. Okay, now at the top of the circle, remember the tension is replacing normal force. Okay, if 3 meters per second is faster than the minimum speed, there's going to be tension in the rope. Everybody all right with that idea? Okay, so what we're dealing with then is that we have, okay, the top of the vertical circle where there's going to be gravity and tension in the rope, but they both act in. Okay, yes, down, but also into the circle, more importantly. All right, so when we say Fc equals forces in minus forces out, there aren't any forces out here. There's 2 forces and they both act in, so we're going to have mv squared over r equals m times g plus the tension. Okay, whereas the last one we did, it was minus. Right? So now, if I want to get tension by itself, what do I have to do with mg? I have to, not divide it, subtract it because I'm adding it in. All right, so that's going to mean that mv squared over r minus mg equals t. And that makes sense. There should be less tension in the rope at the top of the circle than there is at the bottom. Everyone okay with that? All right, the bottom is where you feel heaviest, so there should be less tension at the top. So we've got, okay, the mass still being the same. It's still 1.5 kilograms. So we'll have 1.5 times 3 squared divided by 0.75. And now we're going to subtract our force of gravity, 1.5 times 9.81. And that'll leave us with the tension in the rope. All right, so we're still going to have our 18 here as our centripetal force, okay, because none of those numbers actually changed. But now we're going to subtract, okay, 1.5 times 9.81. So the tension in the rope is considerably smaller. Okay, it's what do we have, 3 significant figures there? So 3.29 newtons at the top of the circle. Right? So a lot less tension in the circle at the top. All right, how many people have done number 3? No? Do we need another minute or 2, or are we just ready to go over it? Another minute? Okay, give me another minute or 2 on number 3. Okay, so now that we're to that point, okay, now that we're solving for V, okay, now we can plug in our numbers. So we're going to have that V equals the square root of, what's the mass of the rock? 0.98 kilograms. So 0.98 times the speed of the rock, which was, we're looking for the speed of the rock, times gravity, 9.81, okay, plus 79, all multiplied by 0.4 meters, the radius, and then divided by the mass again, 0.98. Okay, when we do that, we should get that this thing is moving at 6 meters per second. Okay, everybody all right with that? Okay, now I'm going to go back to question number 2 here for a second, because we're looking at all these vertical circular motion questions, and we're only doing problems that have to do with the top or the bottom of the circle. We've never looked at any questions where we were dealing with the sides. Okay, there's a reason for that. There's no forces to deal with on the side except the centripetal force. Okay? So if I'm looking at the side of the circle here, which way does gravity act? Down. Down. That's perpendicular to the circle. Okay? It's not into the circle. It's not out of the circle. Therefore, it doesn't count. it actually has no effect on the centripetal force in, like if this was something being swung on a rope, okay? The force of gravity has no effect on the rope here or here because it isn't out or in to the circle. So the reason we don't do forces in minus forces out at the sides is because there's only one force, the centripetal force, okay? Okay, and that equals, for this question, the tension in the rope. That's the only thing pulling the pail back into the center of the circle on either side, is just the rope. So we just go mv squared over r, which is why the answer there is 18. That was the answer we got for FC for all of those questions. Okay, now we're going to skip. See if you remember how to do an artificial gravity question. Question number 1 is an artificial gravity question, not a vertical circular motion question. Okay? See if you remember how that artificial gravity stuff works. Okay? Quick reminder, in an artificial gravity question, you're dealing with, okay, a horizontal circle that is spinning at a constant rate. Anybody standing on the inside feels a force against their feet directed towards the center, right? And that force is what we want to have feel like gravity. Okay. If I'm looking at a space station generating artificial gravity, I want the centripetal force to be provided by the normal force, and I want that force to feel like gravity. So Fc equals Fg is the start of this. Now, the problem here is that means mv squared over r equals m times g. But the question wants me to calculate the frequency at which this thing spins. That's not part of this formula, is it? No, but I might remember that v equals 2 pi r over t, which could also be written 2 pi r times f, because f is 1 over t. Okay, we talked about this quite a while back. Okay, f equals 1 over t. Well, this formula here is 2 times pi times r times 1 over t. Agreed? Okay, that's 2 times pi times r times f. All right, can I substitute this in for v in this formula here? I sure can, as long as I do what to everything? Squared. All right, so what that's going to look like then is I'm going to have m times 4 times pi squared, okay, times r squared times f squared over r times, over just r. Okay, because this is now m v squared over r. Everybody all right with that? Now can I solve for the frequency? Yeah, I don't really have brackets here. I was just illustrating that that's v squared. Okay. Pardon me? Yes, that r on the bottom is going to cancel out in just a minute. Okay, so that's going to equal m times g. So this r and this r are going to cancel out. And I'm trying to find the frequency. So I'm going to bring m over to this side. Well, that's pretty cool. It cancels. Okay. Then I'm going to divide both sides by everything else. That's 4 times pi squared times r. Okay, that's going to leave me with f squared, so I'm going to want to square root that. So what I'll be left with is that f equals the square root of g divided by 4 pi squared times r. This is going to give me a really small number. It should. This space station is not going to be spinning around at several revolutions per second. It would liquefy the occupants if it did so. That's why we're getting a decimal here. That means it makes less than a complete turn every second. Don't follow what I mean there. Okay. So we are going to have the square root of 9.81 divided by 4 pi squared times 30 meters. Okay, so the frequency of this rotation is 0.091, or 9.1 times 10 to the minus 2, okay, hertz. Okay. All right. We'll skip number 2, because it's another horizontal one. Okay, I want you guys to write this one down and try it. How fast is a roller coaster traveling through a 35-meter loop if the riders feel 2 times heavier than normal at the bottom? All right, I'm not going to go through the whole thing, but I'm going to give you a little tip here. So we're dealing with the bottom of the loop, and I'm hearing people discuss this, and they're on the right track. Gravity is acting out of the loop at the bottom. What force is acting in? Fn. Okay. Now, it says that these people feel a force that is 2 times heavier than normal. Which force do you feel? Fn. That's your apparent weight. They feel 2 times heavier than normal. Okay, so that means that we have Fc equals Fn minus Fg. Now, how heavy do I feel normally? However heavy you are. Good answer. How do I calculate that? Right, my mass times 9.81, right? M times G. All right, so what we're saying here is that this force is 2 times bigger than normal. This is normal. So what's 2 times bigger than that? 2 mg. That's 2 times bigger than normal. What's 2 mg minus mg? Mg. 2 apples minus 1 apple is 1 apple. We'll go over the rest of that tomorrow.